Hey guys, so today I'm going to work on the Statistical Power Lab in Mod through 3, Section 21. I already started going through the lab. I haven't gone through all of it, so I'll walk you through the bit that I've done and then we'll do the rest of it together. So let's just jump right to the scenario. A researcher wants to study how daily protein supplementation will affect baseline liver fat. So they're going to give them proteins and see if it has any effect on the amount of fat around their liver. The study budget will allow enrollment of 24 patients. Half will be randomized into a placebo, half into the group that's going to get the protein supplement. Trial will be carried over a month. It's desired to see whether the mean change liver fat from baseline differs between the two groups. So they're just trying to see if giving them proteins is going to reduce the amount of fat around their liver. The null hypothesis is that there is no difference between the experimental and the control group change in percent liver fat, meaning that, giving them the protein supplements is not going to do anything to their liver fat, and the alternative hypothesis is that they're giving them the protein supplements will have an impact on their liver fat. They want to know what power will be obtained under the sample size restrictions to identify a change of 0.17. Based on past results, standard deviation of 0.21 will be used. So they want to see, you can't. So when it comes to power, you can push like those three factors to affect power. You can increase the sample size, you can increase alpha, and you can increase the effect size. We're restricted in this case by we can't have more than 24 patients, so n is fixed. So we're going to try to see how we can optimize power. Okay. All right. So let's start off. Number of patients in each group is 12 because we have 24 patients, but we have to split them up into two. One goes into the control group that doesn't get the medicine. The other goes to the group that does. The control group mean, I selected 0 because in the question they say change in mean percent liver fat of 0.17. So they describe that as a change, but they don't tell you what the baseline is. So I'm assuming they consider that the baseline is 0. There's no liver fat or something, and then the change is 0.17. So the control group mean I put in as 0. Let's see if that's correct. And the experimental mean I put in as 0.17. Control standard deviation is 0.21. And the experimental standard deviation I'm also going to put as 0.21. And I want to do that because I'm working on the assumption that we use for for independent t-tests, where we assume that when we're trying to compare the means of two populations, one of the assumptions is that their variances have to be the same. So based on that assumption, I'm going to put the experimental standard deviation as 0.21. Set the number of simulations, put it in 1,000. You can now start running simulations to run an independent t-test with the above data and store the calculated p-value in our p-array. Perform the following tasks. Initialize a NumPy array and fill it with NaN values for storing the results, the p-value of the independent t-test. For a defined number of simulations, do the following. Generate a random normal variable with control mean and standard deviation. Generate a random normal variable with the experimental mean and standard deviation. Run an independent t-test using control and experimental data. Store the p-value for each test. And then we're going to, at the end, calculate the total number and overall proportion of simulations where the null hypothesis is rejected. So we're basically just going to run the experiment a bunch of times. Each time we're going to generate two curves, right? This is going to be, the first curve is going to be our null hypothesis curve. The second is going to be our alternative hypothesis curve. Here the mean is 0. Here the mean for our case is going to be 0.17. And we're going to just try to see, how our power works out and how many times we are able to pick up a difference, I guess. Let's see. Okay. Number of simulations where the null hypothesis is rejected. So we're trying to find out, right? Power is this blue area, because that is when it's the blue area plus I think the red area, right? Because we're going to reject the null hypothesis every time it's either in the blue area or if it's in the red area, because that red area is above the alpha level. So like even though the null hypothesis is going to be true here, we're still going to reject it because it's above the alpha threshold. So basically this whole area is like every time we reject the null hypothesis, which is our power. It's the probability that we're going to reject the null hypothesis, and that's our power. Okay. All right. So random seed, initialize an empty array to store the results. NP empty number of sim. That's the empty array for the size of which is going to be for the number of simulations, and every time we get a p-value, we're going to pop that in there. Okay, we're going to fill it with nans. Run a for loop for range of values in nsim. Okay, so for x and a in range 1 to north sim. So for each simulation, we're going to pull a random variable. Okay, so it's going to be stats.norm.rvs. It's going to pull a series of values where the mean will be the control mean, the standard deviation is the control standard deviation, and the size is 12. So we're going to pull basically 12, we're going to simulate 12 data points that are going to be distributed according to these parameters. Then we're going to create the distribution for our experimental variable, again use the same method, but this time we're going to use the experimental mean, experimental standard deviation, which is the same, and size is also the same. That's going to generate our second curve. And now what we want to do is do a t-test between these two curves to see, yeah. All right, so stats.t-test between control and experiment. And then for px, we're going to store the results 1, right? Results is going to hold the tuple that gets returned from here, which is going to have our p-value and our t-statistic. And then, or the t-statistic and the p-value, and then the second element, or 1 of results is going to be the p-value, and then we're going to store p. Remember, the way that I'm doing it, it's an empty list, right? So, and then now it's just going to pass the x is going to be the index number of that list. So because x is like this, then which simulation we're on. So the first simulation is 1, then 2, 3, all the way up until the number of simulations, which is whatever, like 100 or 1,000. So like basically each time the loop runs through, the list is going to get added. We're going to pull the p-value from the t-test and pop it into that list. Once the loop is done, we're going to have the p is going to be a list of p-values that we got. Okay. Okay, the number of null hypothesis rejections. Okay, so that's where we're going to see, well, how many of those p-values were less than 0.05, right? And what that does is this is going to create a Boolean mask for the list, and then we're going to sum that. That's going to tell us, well, that's the number of times where the p-value was less than 0.05 in our 1,000 experiments. And then the power is going to be basically the probability that the null hypothesis was rejected over the number of times the null hypothesis was rejected over the total number of times that we ran the experiment. And then the power is going to be 0.95, and that sure enough came out to 0.495. So I was like, that's borne out. We don't need to check the solution for that. So the results indicate using 12 participants in each group without giving, so the statistical power is 49%. This can be interpreted as follows. If a large effect is truly present, then the null hypothesis, i.e. that there's no difference at alpha 0.05, would be rejected 50% of the time. Okay, so sample size requirements for a given effect size. Okay, often in behavioral research, 0.8 is accepted as a sufficient level of power. Clearly, this is not the case for the experiment. Determine the required sample size in order to identify a difference of 0.17 or greater between the groups with an 80% power. Okay, so for that, we're going to use, in the previous lab, they gave us a bunch of methods to try that. it's going to be power analysis.solve, right? And what we can do is if we plug in 3 parameters, it'll give us the 4th parameter. Okay. T-test independent power. So determine the sample size. Okay. So we know the effect size, and we want the effect size to be 0.17, right? The number of observations, that we don't know. See, that's the sample size. So we're going to take that out because we don't know what that is. We know the alpha is 0.05, but we want the power to be, what do we want the power to be? 0.8. Okay. To determine the sample size. So, really? It's not. Oh, I didn't import the library. My apologies. Okay. Let's do it properly. Okay. We have to initialize power analysis as an object, apparently. So let's do that. Okay. Let's try that. Okay. So now that says that in order for us to have an experiment where the power is 0.8, meaning that 80% of the time we're going to reject the null hypothesis and affirm our theory, and that taking the medicine will increase or decrease or change your liver fat by 0.17. We're with the alpha level of 0.075, we're going to need a sample size of 544. So that's what we're going to need. Minimum sample size to start the simulations. What does that mean? I don't even know. Okay, determine the sample size. Okay, all right. I don't know what they want us to do here. I mean, we already know what the sample size is. The ideal sample size that we would want. It's the minimum sample size to start the simulations. I don't know. Does it want me to change that? Put that in there. And then the null rejected will be, well, it's 10,000, so we want the null to be rejected 80,000. I'm literally just winging it right now. I have no idea. We'll look at the solution later. As above, perform the following. Initialize an empty array. Initialize a list for storing sample size x power. What? For storing sample size multiplied by power summary? What does that mean? I don't know. While current power is less than the target power, generate distributions for control group given the statistics as before. Run a t-test and store results. Okay. Calculate the current power, output the current sample size and power calculated for inspection. Store the results, sample size, power. Increase the sample by 1 and repeat. No idea what the hell they're saying. Do they want us to increase the sample size until such time as we get there? But we already got what the sample size was to get that level of power. Or do they just want us to analyze how the power changes as the sample size increases, and they want us to plot that out? Okay, and then power is equal to this. Okay, I'm gonna Oh, I think that is what they want. All right, so here's what we're gonna do. Okay, I think that's what they want. Let's see. So let's change that because it's gonna be 0. Okay, and then the sample size is 12. It's gonna start icy. Okay, I think I know what they want. Power sample. So they want both the power and the sample size. Okay, so this time it might be like a. Okay. Empty. Okay. Oh, the target power. Oh, okay. So the current power is less than and the target power is 80. Okay. Generate distributions, run a t-test, calculate the current power. I think I understand what they're saying now. Okay. Output the current sample size. Okay. Increase the sample size by 1. I understand. So they want us to increase the sample size until we hit the power, and maybe to confirm whether that is in fact the sample size that we want. So let's try that out. Okay. Okay, power sample is this, and we are going to initialize an array, and we don't want that anymore because we already have that. Hang on. Yeah. Okay. All right. We don't need that either because we already did all of that. Okay. Okay. So let's wrap this into a while loop. So we're going to say while power is, hang on, did we already have a thing for power? Target. Oh, so we have a target. Okay. So while power is less than or equal to, let's do less than or equal to target, okay, for x in range number of simulations. Okay, well maybe we should wrap all of it into it. Hang on. Okay, store results, list. I mean, do we still do it 1,000 times? Or are the simulations still going to be the same number of simulations as, okay, it's 1,000. Okay, I think we still want to do 1,000 for each sample size. Yeah, okay. So while power is less than target, okay, okay, hang on. All right. Let's tab that over. Okay. So that still comes under our while loop. Okay. Then I think, but then this we're going to want to cut that. Okay, and then put that here. Okay, yeah. So each time we're going to have a new p, which is the p-value, because we need that to that's the probability, and we're going to get our power by using that, by seeing how many times the p-value was less than the alpha. Okay, p dot fill, so we do the empty. We're going to run 1,000. So we're going to run the test 1,000 times at each sample level until the power hits 0.8. Now, if you see up here, the power came out 0.495. Yeah, and that's when we had the sample size was 12, and that's when the power was just. So we're going to increment that size until such time as the power hits 0.8. So let's go down and let's first of all, well, let's declare size explicitly here is equal to 12, right? And then size is going to be equal to size, and then I really should not be using this extension. It's not been helpful. I don't know what's going on. Okay, I need to learn how to use that. Size is size, size is size. Okay. The rest of it, well, the control mean will stay the same, and the experimental mean will stay the same. So will the standard deviations. The only thing that's changing is the size. Okay. Okay. And so this is power. Okay. But we want to also, wait, because we want to keep, okay, and then we want increment size, so the next time the loop comes around, size is going to be plus equals 1. And then what we want to do, wait, no, we want to do that later, because first what we're going to do is we want to put those in power sample. So we're going to, let's do a list of lists. So let's do experiment is equal to a list, right? And the first element of the list is going to be our power. And then the second element is going to be size, right? So we're going to see what power we got for that size. And then what we're going to do is we're going to do power sample dot append experiment, okay, and then increment size, and then yeah, so that's going to do that. All right, so now the way that is going to just, okay, that should work. It's going to run the experiment 1,000 times and then increment size by 1, then do it again 1,000 times, and that shall do it. And then our end result will be power sample. Okay, store the results, increase the sample size by 1, and repeat. And then we want to plot. So plot the calculated power against sample size to visually inspect the effect of increasing sample size. So that's what they're trying to get us to do. I mean, they could have been more. Okay. All right. So let's just populate that. Let's see what happens. Here we go. And it did not go. Okay. Target. Oh, we didn't define target. Yes, we did. Oh, I just didn't hit Shift Enter. My bad. Okay, let's do it now. This might take a while, guys. Is not supported between instances of what? Oh, wait, what? Power analysis. Where? Are you crazy? Oh, it's not crazy. I'm the one who's crazy. Okay. So let's explicitly redeclare power. Or should we change what it is up here? Where was it? Hang on. Experimental P. Okay. Yeah, I was lazy. I should have done it differently. Power testing. Let's rename that variable. Okay. And oh, I don't even need that at all. I'm so silly. This is what happens when you blindly copy paste code without really looking at it. You know, it's a bad idea. Never works. You should always carefully see what it is you're pasting and what it is that you're doing. Okay, let's try it again. Oh my God, what are you doing now? It shouldn't be a thing anymore. Oh, because it's in memory, it's still that. Okay, so you know what? I'm just gonna explicitly let's just make power equal 0. No, just 0. All right, it's running. It's gonna take a while. In the meantime, what should we do? Okay. It seems to it's still running. All right. Invalid warning value encountered unless, I don't know what it means, but it's still running. I don't know. Let's see what happens. Power sample is a list. It's got 72 elements. Why is it still running though? Well, no, that's a size. I don't know how the variable inspector works. I think it only updates after it's done running. It's going to take a while because we're running 1,000 experiments like 500 times. So I think it might take a bit. I don't know. Should I pause the video? I'll pause the video. Okay, so it finished running, and let's see what it did. So plot sample size x power line graph. So we want to plot basically the sample size is going to be on the x value and the power is going to be on y. So let's just do, well, let's do a data frame. Power sample df is equal to pd.data frame, and I don't know if I import pandas as pd. Oh my god. I'm going to disable this thing. Dot data frame, and we're going to pass into this power sample and see if that works. Okay. No, we're just going to do power sample. Okay. Improt. What is improt? Silly Omar. Okay, I'm just going to do a display of that. So display power sample df. Okay. Alright, so that seems to be... Why is it so small? Well, it isn't. It makes sense because as soon as it hit 0.8, the power, it stopped. So the sample size of 26 was sufficient. So why did I get 544 here? Maybe I did that wrong. Is that what I did wrong? Determine the sample size. Hang on. I'm going to go back and see what Statistical Power Lab. No, I want to see Statistical Power. Okay. I don't know. It's I mean, even in here, the sample size is pretty large when they try to use the method to figure out. Yeah, see, calculate the sample size required. So the effect size is 0.2, alpha is 0.05, power is 0.8, and the sample size came out 393. And we had like even a slightly lower effect size, so which is why our sample size was like a touch higher, 544. So I don't know exactly what that's doing. I mean, according to this thing, you need a sample size of 400, 500. But when we ran the simulation, it seems to say that if you give 26 patients or 26 subjects, that's enough for you to get the power that you need. But anyways, let's plot this out. Power sample dot. All right. Power sample df dot plot dot line. X is gonna be. Well, let's just do that. See what. Okay. I don't know what the hell that's doing. Okay, maybe we should just explicitly tell it what to do. Okay, so X is going to be, oh, right. What's the first item is, okay, power is 0, and we want power on Y, so size is going to be on X, and that's going to be on Y, and that did nothing. Damn it. Hang on, I'm going to pause it. Alright, so I managed to plot the thing. Powersample.df, plot.line. The x-axis is 1 because that's our sample size, and we want that on the x-axis, and on the y-axis we want power. So yeah, sure enough. So when we look at the line, we see that, like, you know, increasing the sample size up till 20, you know, huge change in power. After that, you have diminishing. Like the rate of increase in power like kind of slows, the curve like flattens out, and then you hit 0.8 once you have 26 people in your sample. So it seems that 26 people is the ideal sample size to have in this situation to get a power of 0.8. Okay. You would need a considerably higher number of patients. And again, I could be entirely wrong. In a second, we'll look at the solution and see what they say and see if I was wrong. Should we do the bonus? Bonus, investigating the relationship between power, sample size, and effect. Okay. Interesting to plot between power and for different effect sizes. To do this, run multiple simulations for varying parameters, store the parameters, and plot the resulting data set. Specifically, use a value of alpha for all, use the following effect sizes, use sample size from 10 to 500. Okay, for each effect size and sample size combination, calculate the power, plot the line graph. Alright, what the hell, let's do it, because they did this in we can just copy paste a lot. I'm going to shift it to my second monitor so that I can do that. Okay. Oh yeah, because there's like an easy method, so you can do the power analysis dot plot. Although of course I think we renamed. Did we rename this variable? Power analysis. Where did it go? Yeah, power analysis. Okay, yeah, that's the TT test independent power. Okay, so we have that object in there. So the dependent variable is going to be what the hell was that? Knobs. What was knobs? Is that just the name of it? Oh, wait, the dependent variable. Number of observations. Okay, I think that's what goes on the x-axis. Okay. And then knobs is equal to, okay, np.range. Well, let's change this because it says 10 to 500. We're going to do 10 to 500. And let me remember how you do the increments. Okay. That's going to be 10, right? Use sample sizes. Wait, we don't need to. Why am I even bothering? Let's just do 10 to 500. Effect size is, let's just copy this list. Okay. Alright. Alpha's going to stay the same. Okay. Let's see what that does. Huh, look at that. Okay. Okay. Yeah, that's showing us, yeah, it seems right. It seems similar to what we saw in the lab here, right? Let's just pop that there. So yeah, here, yeah, they show you the same thing. Like, the whole idea is to show you that, like, you know, as the effect size gets bigger, the power can increase without needing too large of a number of observations. And the effect size, again, is to see, is basically, so like in the case of the example where they're trying to look at, well, what's the change in liver fat between like a normal population and the people that took the medicine? If you take the medicine and, you know, the change in your liver fat is like really small, it's going to be harder to distinguish whether or not, you know, your slight change in liver fat is just random chance, because like people will have random variations in the liver fat anyways. But if the medicine is like super powerful and it's going to like dramatically reduce your liver fat percentage, then that'll become more obvious, right? The curves will like shift apart, and, you know, the effect size is greater, and that's, you know, so the power will increase. Similarly, if, you know, on the other hand, you can also increase the power by increasing the number of observations, right? But like, so in this first scenario where you have the highest effect size, which is 0.5, you don't need to increase the number of observations a lot in order to max out the power of your test. But if the effect size is really small, then you're going to want to have to run that experiment on a large sample size of people. And even then, like, if they're for the really small, it's going to be barely noticeable. But like, so this middle ground, this pink one, which is like the effect size is 0.15, that's kind of a small effect size. It's going to be hard to tell. So yeah, all right. Oh, let's look at the solution. Now, let's see if I got it right. I like this part. This is fun. I'm going to do a side by side. Okay. I am done. Yay! Okay, let's do the solution. And let's compare. Okay. There's no difference. Okay, so let's see. Yep, they set the control mean as 0 as well, as did I, so I was right in making that assumption. Experimental mean is 0.17. They got that right. So then let's go down to the next one. Okay. How do they do it? For S in range, number of simulations, the control is random.normal. I use RVS. I guess they don't, and I don't know what that does. Oh, right, because RVS will bring you actual values, whereas that just calculates. I think it brings you the equation for the normal distribution that you plug in. I don't know. And then, yeah, that object is just like the parameters of it without actually giving you the values, I think. Same thing down here. Right, they put in the experimental mean, standard deviation, and the sample size. And then they run a t-test, same thing, stats.t-test, both of them. And then they do the same thing, right? Like PS, I use X, they use S. It's the same idea. They use the index to like increment the position in the list, and then to that they will add t-test 1. They call it t-test, I call it results. Same thing. And then, yeah, same thing down here. Number of null rejected is np.sum, where p is less than 0.045. Yeah, Boolean mask summing up. And then just do a fraction of that over the length, over the, float and sim. I do length of the list. I think it leads to the same result, 0.495 and 0.495. So yay, I got that right. I get a gold star. Uh, guys, it's 1 o'clock in the morning. I'm just having some fun. Okay. Let's see now. So did we get this part right? Okay. T-test independent power. Power dot solve power, right? Why did we get that 544? Okay, what did I do? Dot solve power, effect size is equal to 0.17 over 0.21. Why are they doing 0.21? That's weird. What's the point of that, I wonder? I don't know why they would do. Why would they do that? What the hell is 0.21 was the standard deviation, right? Yeah, that's the standard deviation. So why are you dividing the effect size by the standard deviation? I don't remember what that did. Oh, that's the Cohen's d. Okay, because I didn't explicitly calculate the Cohen's d, and I think that the Cohen's d is the difference in means divided by, well, let's double check. Do I have that in my outline? Here, let's look at my nifty little outline. Let's see. Type 1 and type 2 errors. Where is Cohen's d? Let's navigate to statistical power hypothesis. Effect size. Cohen's d. Okay, Cohen's d. That is the effect size, which is the difference of means over the pooled standard deviation. Okay. Which is the weighted average of the standard deviation. There's a complex calculation for that. And then we take the square root of that to get the pooled standard deviation. Okay. Okay, so the effect size has to be specified as Cohen's d. The mistake that I made was I just plugged in the raw difference of means. But also from this, what I'm gathering is that when the standard deviation, when the two distributions have the same variance, then you don't need to do the pooled standard deviation, because they don't, right? Like in our in this one here, they're not doing that. Yeah, right. Okay. Yeah, they just do 0.17 over 0.21. They don't seem to be calculating the pool standard. So I guess when the two distributions have the same standard deviation, then we don't bother doing the pooled. All right, you learn something new every day. Something maybe I'll run by James or somebody and see what his thoughts are on this. So that says 24. All right. Okay, so the sample size 12, null rejected 1,000. Just leave that there. Okay, and then let's see how they do this. Okay. P is equal to NP dot MT dot number of simulations. Okay. So while no, but they do the same thing, right? So they don't seem to be doing it each time, or do they? How they're doing it slightly differently. Let's see. Creates an array of nsim number of arrays, each containing the sample size number of elements, manually looping, but is much faster. So they did it way faster somehow. Okay, that's what I did. Okay, yeah, that makes sense because it took me a while to run. Okay, np random dot normal. Okay, np random dot normal. Okay, for the experimental, the results they do the t-test p-vals. Find the number of rejected. Okay, and increase sample size by 1. Okay, but the results seem to be the same, basically, like pretty much, with like slight differences. So I ended up with 26. They ended up with 25 being the ideal number of samples. But I think that might just be a function of the fact that I was pulling random actual values, and they were doing it using their method, which is alright. It'd be fun to sort of try to parse that out more and see how they're doing it. But I think I got the answer right, so I'm just going to keep moving. Yay. And then you look at their chart. It looks about the same, don't you think? Yeah, about the same. So I'm happy. And let's see further with the bonus. They also, again, use their wonky thing, and I used this. I feel like it demonstrates the principle sufficiently. Oh, I think because they did it by rerunning the experiment, and I basically just plopped in the thing that they showed us in the README. But it demonstrates the principle sufficiently, right? Like sample size, it goes from here to 500, power 0 to 1. The reason theirs is jagged is because they're actually pulling actual values, I'm guessing, and they vary, but they generally trend in this direction according to this, and I just do, I don't know what I do. Alright, so that was the Power Lab. I hope that you enjoyed it. It's 42 minutes long, which might be way too long to write to make a thing for, but I don't know. It was fun. Alright, guys, I hope you liked that. This is Omar. Peace.